Today is a special day because today we're going to walk through the thought experiment of a Danish mathematician, Caspar Wessel. Wessel was thinking about numbers one day, and as he was wont to do, and he had this idea: what if I could invent a number that expressed not just magnitude or how much of something exists, but gave magnitude and direction? This was a novel thought. If we think about numbers the way we do normally, if we think of, say, the number 3, all that really means is that there are 3 things there, like 3 stones. Or if we're looking at a number line, it means we're 3 units away from the origin. What he wanted was to make a number that could express not just how much, but in what direction. Now you might be thinking, we kind of already have that with the Cartesian coordinate plane, right? We can represent this point here with a 2 for the x and a 3 for the y, but that's not one number. That's 2 numbers to represent one point. What Wessel was after was one number to rule all of them, to give both distance and direction all at once. And so he did what mathematicians often do. He realized that this kind of number doesn't exist in our world. So he made it exist, and he invented something. And he said, I'm going to invent a new kind of number, and that new kind of number, that new unit, is going to represent a 90-degree turn. So one of this new kind of number represents a given direction, namely a 90-degree turn. Now, he did use the Greek letter phi. This is not to be confused with the golden ratio, but I'm going to continue to use phi because that's how he wrote it in his paper. All right. So if we look at a normal Cartesian coordinate plane, phi does not show up. There is no phi axis. So Wessel had to make up his own kind of coordinate system, one that had the numbers we're not used to seeing, like 1, 2, -1, -2, etc. But then he had to make a new kind of axis where phi could live. All right. So since phi is a 90-degree turn, he made this point here on this vertical axis, 1 phi, and then this point obviously is going to become 2 phi, etc. Okay, so let's just make sure that this makes sense so far. If we wanted to represent, say, this point here, right, at the 1 on the real number axis, we haven't turned at all. So that's the same thing as 0 phi, right? So we can have 0 phi, just representing that 1, right? So for right now, I'm going to be focused more on direction rather than distance. So maybe I should just ignore this for right now. And we're just going to call this kind of our starting point. All right. So then if we have 1 phi, I stopped the video, but that was a good take, so I'm going to keep it. If we want to represent this point, well, that is exactly 1 90-degree turn, so that's just going to be written as phi, all right? And phi, again, is a 90-degree turn. 0 phi is 0 degrees. Making sense so far? All right, so now what if we wanted to represent this point over here? All right, well, how, again, express all of these points in terms of phi. Well, that is the same thing as 1 90-degree turn and 2 90-degree turns. So phi squared. We're not going to call it 2 phi because 2 phi means 2 units in the phi direction. So this is really phi squared. Phi squared is 180 degrees. Good so far? So let's keep going. If we wanted to represent this point down here, now it stands to reason that if these are 1 and 2 and 3 phi, then this would be negative phi, negative 2 phi, right? So again, in terms of phi, how do I get here? Well, I'm going to have to go one 90-degree turn, a second 90-degree turn, and a third 90-degree turn, or phi cubed, which is essentially a 270-degree turn. All right? Now lastly, if we want to make a full revolution, end up back where we started, in terms of phi, we're going to have to make 4 of these quarter turns. 1, 2, 3, 4. So phi to the 4th is 360 degrees. But 360 degrees is also the same thing as 0 degrees. So in a weird way, 0 phi is kind of the same thing as phi to the 4th. All right. So let's just kind of stop, take stock, and think about what this means. This is what we mean by phi. We can get to these different places in this new kind of space in terms of direction, using this new kind of number. But now that we have a good understanding of this, the question is, what is it? What is phi? Can I make any kind of numerical sense out of it, right? Or is it just going to forever remain this weird symbol? Even pi, I mean, it's a symbol, but it has some numerical sense, albeit infinite and non-repeating, 3.14 and blah, 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 blah. So that we can make some numerical sense out of. What about phi? Other than just 90 degrees, can we make some sense out of this? All right, so now we're going to kind of go back through this, but in addition to thinking about direction, think about kind of where we are in relation to the origin. So let's take the first one first. So we saw that, actually I'm going to write it over here. So phi well, phi is its own unit, and so it cannot be expressed in anything else. So it's really, just the one version of itself. Phi squared, however, think about where we end up at phi squared. We end up at -1 on our number line. Okay? Now phi cubed. Phi cubed took us 3 turns, and we ended up at -phi. All right, so these two expressions are equivalent. And then lastly, phi to the 4th gets us at +1. All right, things should be getting a little bit weird right now, because I made up this number, or rather Wessel made up this weird number that represents a quarter turn. And yet, when this strange number, good Lord, when this strange number is squared, we get a real number as the result. Then when it's raised to the 4th power, we get another real number. This is weird. Can we make any sense of what phi must equal given this, right? Hopefully, you zeroed in on the first instance where our fictitious number, our made-up number, got us something that we're familiar with. Focus in on this equation here. Phi squared is equal to -1. I'm going to rewrite that over here. Now, this hopefully should look simple. We have a variable, phi, and a real number on the other side, which means we can solve for phi. And we can do that pretty easily, right? if phi squared is equal to -1, then all we got to do is square root both sides, and we get phi. Phi is equal to the square root of -1. Now, when we were dealing with roots and radicals before, we determined that this kind of expression is nonsense. There is no number that when multiplied by itself gets us -1, which is precisely why it's popping up right here. There was no number in the universe that we could have used to express direction, because in the real number system, it's nonsense. We can't do it with real numbers, so we needed a new kind of number. We needed an imaginary number. Phi, this number that Wessel invented out of thin air, ends up being equal to the square root of -1, which is more commonly known as I. Okay, so this, hopefully things are starting to come together a little bit. This directional number is the imaginary number. Now, I acknowledge that this is horrible PR. I really hate the name imaginary number because imaginary makes it seem like it doesn't really exist. But imaginary numbers are actually incredibly useful. It's only because of imaginary numbers that Einstein was able to make his general theory of relativity, and it's the only thing that really helps us make sense of the space-time continuum. It turns out that physics, modern physics, quantum physics, is impossible without imaginary numbers. And again, this started off as just kind of a wonky idea of inventing a number that could express direction. But let's see if this idea is consistent with what we have over here, that phi is equal to the square root of -1. I'm going to have to erase some things. Hopefully this is okay. You can have the advantage of rewinding the video if you need any of this. Alright, so let's take the first one first. But every time I see the symbol phi, I'm going to write the square root of -1 instead, or I, right? So I is just equal to I, which is equal to the square root of -1. All right, there's no mystery there. Again, this is our new unit. This is a new kind of number. This is an imaginary number. And so it cannot be expressed in any other terms than that. But then if we get I squared, all right, so that's the same thing as I times I, which is the same thing as the square root of -1 squared, all right? And now if you square the square root of something, those two operations cancel each other out, right? So that square cancels out the square root, and we just get -1. And that's precisely what we got over here. Phi squared gets us -1. I squared gets us -1. Now what about phi cubed? Well, it's the same thing as phi squared times phi. And we already established that phi squared is equal to -1, so it's really just -1 times I, or -I, which again is exactly what we expected. Phi to the 4th, well, it's the same thing as phi, or I squared times I squared, but I squared is equal to -1. So it's going to be equal to -1 times -1. And the two negatives cancel out, and we get +1. All right. So this seems to be consistent. It matches up with what we expected back when we were in this theoretical phase. Excuse me. And the math checks out. And then if we were to go anywhere beyond this, like I to the 5th, all right, well, it's the same thing as I, because I to the 5th is the same thing as I to the 4th times I, but we already established that I to the 4th is just 1. So I to the 5th power is 5 quarter turns, which is really just the same thing as 1 quarter turn. All right. Now, let's take a step back and look at what we've accomplished so far. Wessel invented a new kind of number that could express both magnitude and direction. He started off calling it phi, and then after kind of establishing what that means, was able to deduce that phi is equal to the square root of -1, thus giving birth to what is now called I. So what does this look like if we go back to our kind of plane over here? When I is, or an imaginary number is joined to a real kind of number, we call that a complex number. And if we look at our plane over here, the horizontal axis is real, or the real numbers, and the vertical axis are the imaginary numbers. Again, just replace the phis with i's. So if we took a complex number like 2 plus 1i, right? This 2 is the real part, and this I is the imaginary part, right? Making this a complex number. Right? So what does that look like over here? It means that we're going to go over 2 units on the real axis, and then we're going to go up 1, or a quarter turn, in the imaginary direction. That point is 2 plus I. It has magnitude, how far away from the origin, and it has direction. And I can represent any point here using a real and an imaginary part of a complex number. What I really like about this is that if we think back to what he was doing in the first place, Wessel wanted a number to have both magnitude, how big it is, and direction, where's it going. Essentially, what he's making is a 2-dimensional number. He wanted a number that gave 2 bits of information, or 2 dimensions of information. We've never really thought about our normal numbers as being 1-dimensional, but Wessel challenges us to think of them in that way. Normal numbers are just 1-dimensional. They just say how much. His new number is 2-dimensional, giving us distance and direction. I think that's lovely. But of course, this makes one think, could there potentially be 3-dimensional numbers, or 4-dimensional numbers, or more? Well, the answer is yes. Because again, in mathematics, if something doesn't exist, we can just make it exist. But we'll deal with that at another time. I think that's sufficient for the evil of this video, and we'll be back shortly.
I can't run too farther. I need love. I can't talk to you, mother. I know it's got you caught up, but your sweet sinless sensation is not my style, and I'm not giving up. But tell me if